Okay, so I've just collected homework 2A. You can see here's the assignment for homework 2B. It'll be due on Tuesday. Now that I know that you're working from the old book, I'll make sure that, don't start on these until you hear back from me. I'm going to have to review to make sure that that's not a bunch of crazy problems, because it could be that some of them are. I'll send an email today that says, go with this list, or here's a modified list. Yeah. All right. So you'll hear from me today with the updated description of that, since you're all using the 9th edition book that they're selling in the bookstore. All right. So we're going to talk about surface tension and some fluid properties that relate to pressure. Where we left off, last time we were working this example when we ran out of time, and so we'll pick back up on that. What we had was a room, a 4 by 5 by 6 meter room, and we're calculating the density, specific gravity, and the mass of air in the room. And I think where we had already gone to was substituting some variables into the equation for density. Pressure divided by the gas law constant R times T. So it's 100,000 kilogram second squared times meter is the pressure. The R value, 287 meters squared per second squared Kelvin, and then the temperature of 298 Kelvin. So the density of air in the room, 1.169 kilograms per cubic meter. Now you may be wondering why some of these units are so strange, like the units of pressure. Ordinarily the pressure that we'd say is pascals is a unit of pressure, and a pascal is the same as a Newton per meter squared. So what we did to get to these weird units is we said, well, what's a Newton? It's a kilogram meter per second squared. So we expand out the units into its fundamental underlying units. And so every unit that's out there has been based on length, mass, or time. So length being meters, mass being kilogram, time being seconds. And so joules, watts, newtons, all of those are just various combinations of length, mass, and time. And here what we did was we took the R value, for example, and we converted it into units of length, mass, time, and I guess we could say also temperature, since Kelvin is a measure of temperature. All right, so that's how we got this density of air in the room. Specific gravity, remember, is defined as the density of something relative to the density of water. And so here we want to find out what's the density of air relative to the density of water. 1.169 kilograms per cubic meter. And the density of water, 1,000 kilograms per cubic meter. And so the specific gravity is 0.001169. All right, and finally, the mass of air in the room. In order to find the mass, we have to start off by knowing the volume of the room. The volume is just simply going to be 4 meters by 5 meters by 6 meters. And so that means that the total volume of air in the room is 120 cubic meters. And the mass of air in the room is going to be the density times the volume. So that is the 1.169 kilograms per cubic meter times the 120 cubic meters. So that is 140.3 kilograms is the total mass of air in the room.
In the book it says gamma. Should we use like that, or does it just
Specific gravity? It can be the ratio of densities or the ratio of gammas. So it could be gamma of air relative to gamma of water. And that's also another definition of specific gravity. I think it says as much in one of our earlier slides, that it's the ratio of either. Because gamma is simply it's G times the density. And so if G is in both the numerator and the denominator, then it cancels out. So both work. Other questions from this example? All right. Here is a car, and it's pictured just to illustrate that the pressure in the tires. What's a typical air pressure for tires? What do you usually fill your tires up to? 32, 34. Maybe if you've got a truck, you'll put in more than that. All right. When you say that the pressure in the tire is 32 psi, without even saying it necessarily, you're already saying that that's relative to atmospheric pressure. You're implying that that's relative to atmospheric pressure. That's not the absolute pressure of air in the tire, but that's how much additional pressure is in the tire compared to our Earth's atmosphere. And so one important thing that we have to differentiate between is gauge pressure and absolute pressure. Now, let's say that you had a perfect vacuum inside of a tank like this, that it had been completely evacuated of any air. There weren't any gas molecules at all inside of that tank. Well, if that was the case and this tank was in the Earth's atmosphere, then the Earth's atmosphere would be pressing on the tank with 1 atmosphere. There would be nothing inside, and so it would have gauge pressure of 0 inside of the tank. It would have an absolute pressure of 0, and it would have a negative gauge pressure because it would be lower than the Earth's atmospheric pressure. Let me show you a diagram that kind of illustrates this. Now, the definition of absolute pressure is just we're saying that we're measuring the pressure relative to a perfect vacuum, or how much atmosphere there is in space. None. In Huntington, for example, the absolute pressure of the air is 14.7 psi, and the little a there in the subscript, that means absolute. The absolute atmospheric pressure is 101 kPa. In terms of millimeters of mercury, it's 760 millimeters of mercury is the absolute pressure. My tires, therefore, if I fill up my tires to, let's say, 32 psi, then you add the tire pressure to the absolute pressure of the atmosphere, and so the absolute pressure in my tires, 335 kilopascals. So it's like what we're measuring against is the operative difference between atmospheric being the gauge point or vacuum being the gauge point. So gauge pressure is when instead of using vacuum as the reference, you're using atmospheric pressure as the reference. And so if the gauge says 0, that doesn't mean that there's a perfect vacuum. That means that it's measuring against the air pressure that surrounds the tire. And so my tires, if I fill them to 34 psi, are going to register 234 gauge pressure. So there's absolute when you're measuring relative to the vacuum, and there's gauge. And so just consider that if you had a graph where vacuum is below atmospheric pressure, and they're differing by 101 kPa. And so atmospheric pressure is 101 kPa above vacuum pressure. So then my tires are going to be having an even higher pressure than atmospheric. If I measure my tire pressure from the vacuum, then that absolute pressure is 335 kPa. But if I measure it from just the gauge, if I want to know the gauge pressure, then I use the starting point for measuring as atmospheric pressure, and it's 234 kPa. So if you want to know the gauge and you've got absolute, subtract atmospheric pressure.
So if your tire's at 101,
Unless that was gauge. If it was 101 gauge, then it wouldn't be flat. But yeah. If you had a measurement of your tire pressure and it was an absolute measurement of tire pressure and it said 101, then it would be flat, because 101 would just only be measuring the atmosphere. All right. So let's apply that to another gas law example here. If we have a tank of oxygen, it's 25 cubic feet is the volume of that oxygen tank, and it's pressurized to 650 psi, and we know that the tank materials themselves, just the steel that the tank is made out of, weigh 50 pounds of force, and that the temperature of the gas is 120 degrees Fahrenheit. What's the total weight, meaning the weight of the tank and the weight of the gas that's inside? So we know the pressure, the temperature, the tank volume, the tank weight, the R value, and then remember from the previous example we worked, here's how you can calculate the density of a gas. So what I'd like you to try in this example is calculate the density of the gas, and then when you know the density of the gas and the volume of the tank, find out the total weight of the oxygen that's in the tank in addition to the tank material. And of course, you can work with a partner on this as you work through the examples. You can always talk it over with a partner. One important thing that you need to do is make sure that your units are consistent. And so if the pressure is given in 650 pounds per square inch, then you need to convert that into pounds per square foot by multiplying by 144. So there's 144 square inches in a square foot, so that's why we multiply. And that gives us that the pressure is 93,600 pounds of force per square foot. Dividing that by the R value for oxygen in traditional units, 1555 foot-pounds of force per slug Rankine, and multiply that by 580 Rankine, the temperature. From previous lecture, we know that the conversion is temperature in Fahrenheit plus 460. So it's 120 degrees Fahrenheit plus 460. That's where the 580 Rankine comes from. Okay. So all of that gives us that the density of the gas is 0.1038 slugs per cubic foot. And that's the density of oxygen at this pressure in question. So then if we multiply the density by G, that takes it from slugs per cubic foot into pounds of force per cubic foot. So it goes from a density to a unit weight. Or sometimes this is called unit weight, sometimes it's called specific weight, gamma. So we know the gamma of the gas, 3.342 pounds of force per cubic foot. Now we can find the weight of the oxygen inside the tank by multiplying the unit weight by the volume that's there, the 25 cubic feet. That means that there's 83.6 pounds of gas plus the 50 pounds of the tank weight, means that there's 133.6 pounds of force. That's the combined weight of the tank plus the gas. All right. Any questions from this? If not, then we're going to move on to talk about surface tension. Take a look at this picture. What's happening in this photo? We've got a bug. What's the bug doing? We assume he's walking on water, or she. It could be a female bug, right? Walking on water. You've probably seen things like this, water bugs that are able to walk on the surface of liquids. And why is that possible? How is it that the insect is able to walk on water? We can't. Why can the insect?
They don't have enough weight to produce surface tension.
All right, what is surface tension? You're right, but what is surface tension?
The interaction of the hydrogen molecules together, they attract each other.
All right. Yeah, the water is attracted to itself. And so, what is it, how is this bug, the bug weighs less than us, but it's not only about the weight of the bug, it's also about the length of its feet. If you look at the the length of its feet, that's another important aspect of this. And you can see that it looks like there's some curvature of the water around the feet. Let's take a look at a brief video clip that illustrates this same effect. Watch as drops of water are placed onto a penny. Water is attracted to itself, and because of that attraction, you can get quite a lot of water onto a penny. There's a membrane effect on the outside of the liquid that keeps it together. It's almost as though it's in a little plastic bag. That membrane effect keeps everything together. So surface tension, this attraction allows for the bug to be walking on water. It happens because the bug doesn't weigh much. It's spreading out its weight, and the downward forces of the bug spreading out its weight over a relatively large area are less than the effects of surface tension. The surface tension is wanting to keep the water together, and so it's resisting anything from penetrating the membrane, that same membrane that we saw surrounding the pennies. And that's what allows, for example, a paper clip to float. That's something that any one of you can do. You can watch a paper clip float. Steel definitely is more dense than water, and steel will sink to the bottom of it once it breaks that membrane. But in the case of a paper clip, it's spreading out the weight of the paper clip over a very wide area. And it's because of the attraction of water to itself. Water is a polar molecule, meaning that the negatively charged oxygen is going to be very strongly attracted to the positively charged hydrogen. And as a result, at the top of a water layer, there is sort of an added attraction, because if you think about what's happening to the water molecules that are under the surface, that attraction can be expressed to a greater number of molecules. Like, look at this molecule right here, how many molecules are adjacent to it. There's one on every side, there's one beneath, and there's one above it. And so it has a certain amount of attraction that it expresses to 4 adjacent molecules. But the molecule that's at the top, at the interface of the air and the water, it has that same tendency to bond with other water molecules, but it doesn't have as many near it to bond to. It can bond to the ones that are on either side and the one below, but because there's not a molecule above it, it has an even greater attraction on a unit basis than the water molecules that are down beneath. And so it sort of acts as a membrane, that extra amount of attraction that's at the interface of the air and the water. Now, surface tension is a fluid property, and different liquids have different amounts of surface tension, and in fact it varies as a function of temperature. You'll see that water is listed at a variety of different temperatures, and 0.073 is the room temperature surface tension of water in terms of newtons per meter. And it has units of force per length, which is significant because of the equations that we put it into. You'll notice that mercury has a very, very high surface tension. And you can basically pile mercury on top of itself even much more distinctly than the example that we just saw of the penny having water drops accumulate on the top of the penny. So this membrane effect is what causes the bug to walk on the top of the water, or the steel paperclip to float. And it varies as a function of temperature, and we can find the magnitude of the force of surface tension by multiplying the surface tension constant by the length over which the surface tension acts. And so in the case of the bug, for example, if we want to know what sort of surface tension force the water can resist. You know, how heavy can the bug be? What you do is you find the contact length, and by the way, for each leg you double it because there's a left and a right side. You know, there's basically two places that the water is being bent on either side of that. And if I drew a cross section of what I mean by that, there's the bug's leg, and here's the water being bent, and so there's two places that the water is being bent. And so if you find the relevant length, that would be the sum of the lengths where the bug's leg is in contact with the water, and then you double it. All right. Now, related to surface tension is something that's called the capillary effect. Now remember that surface tension was the principle that water is attracted to itself because there's hydrogen, there's oxygen, that's a highly polar compound. Well, in addition, water is attracted to oxygen molecules in a glass tube. A glass tube is made out of SiO2, silicon dioxide, SiO2. And so in the same way that water is attracted to itself, water is attracted to glass, and it wants to maximize the contact area that it has with glass. And so if you drop a glass tube with a small diameter down into water, then the water will be sucked up into the tube. And that's called the capillary effect. And it's surface tension forces that pull it up into the tube. Now we have a couple of different parameters we have to measure. First of all, there's a contact angle that for water we can assume is very close to zero, or it is zero. For other liquids there'd be a different contact angle. The tube diameter is relevant because the smaller the diameter of the tube, the higher the water level will actually rise up in the tube. In just a minute I'll show you mathematically why that is. The force of surface tension, the force that water is being pulled up inside the tube, is a function of the diameter, the surface tension constant, and the cosine of the wetting angle, or the contact angle. Although the force due to surface tension decreases as the diameter gets smaller, then the force pulling it up decreases. So does the weight of the water. And we'll illustrate that in just an example here in a second. So the way that you'd find delta H, if you're trying to find how high the water level will rise in a tube, you have to know what the force of the water is. That's a function of the diameter. So let's illustrate that with this capillary rise problem here. Let's say that we have a glass tube that's got an inside diameter of 1.6 millimeters. We want to know how high the water level is going to rise in that tube. This is a force balance problem where two things are going to be in equilibrium. The weight of the water is going to be in equilibrium with the force of surface tension pulling the water up inside of the tube. Okay, so these two things that are in equilibrium with each other, we need to calculate both of those. So the weight of the water. How do we know what the weight of the water is inside of the capillary tube? That is basically just the volume of water that's above the free surface elevation of the surrounding water. These little hash marks here, those are meant to represent ripples, meaning that it's in contact with air. And so here we have water that's in contact with air, and then a glass tube that goes down into it. And so when we put that glass tube in, then that causes the water level to rise up to a certain elevation here. And so then this little triangle is another way of representing that it's in contact with air. Same as those little ripples, that's what that triangle means. Or sometimes you'll see a triangle with a couple of horizontal lines underneath it. That means that it's air touching water. So we've got a glass tube. The diameter here is 1.6 millimeters. So what is the weight of the water that's above this water line here? How can we find that, the weight of the water? How did we find the weight of the gas in the previous example? When we found the weight of O2, what was the formula for that? What was that? All right, it's actually going to be the volume times the gamma. So the unit weight of the fluid times the volume of the fluid. So if we want to find the weight of the water here, we need to know it's going to be the volume times the unit weight for water in this case. Okay, so the volume for this tiny little element of water that's being pulled up is going to be delta H is the height of it. It's a cylinder of water because this is a circular tube, and so the shape of it is a cylinder. And so the volume is going to be delta H times pi d squared divided by 4. That is the cross-sectional area. And by the way, you may be thinking usually the area is pi r squared. Most of the time in hydraulics and fluid mechanics, we refer to things by their diameter rather than by their radius. It's just sort of the common way of sizing pipes, for example, is to refer to their diameters, not their radius. And so this is area, pi d squared divided by 4. So I don't think you'll see pi r squared in any of the examples that I work just because it's the typical thing to refer to things by their diameter. So here we want to find what's the weight of the water. It's going to be for 20 degrees Celsius, then the unit weight of the water is 9790 newtons per meter cubed. We can look that up from the table in the book. At 20 degrees Celsius, table A5 tells us 9790 is the unit weight. So we can calculate then what's the weight of the water inside of the capillary tube. Pop out our calculator here. Okay, delta H is unknown. The area, pi, and the diameter is going to be 1.6 millimeters divided by 1,000 millimeters per meter squared divided by 4. Okay, so the weight is a function of the unknown delta H. So we're going to have that staying as an unknown. The other thing that we know is that we can calculate the surface tension. The surface tension is going to be equal to the length times the surface tension constant. Okay, so surface tension constant, pi d cosine of the angle. Now, in the previous slides, pi d is the circumference around the tube. That's the length that gets used in a glass tube type problem. Like here it says that the surface tension force is the surface tension constant times L. In the case of the bug, it was just the length of the bug's legs. But here, the relevant length is the circumference around the outside of the glass tube. And so that's why we're using pi d, is that's the circumference of the glass tube. All right, so what we can do is we can rearrange all of this to say that if we have the surface tension minus the weight of the water is equal to 0, then that means that the surface tension constant, pi times d cosine of theta minus gamma delta H and pi d squared divided by 4 is equal to 0. So the weight of the water is going to be in equilibrium with the surface tension forces. The water level will rise because the surface tension is pulling the water up in the glass tube, but then it will stop when the surface tension force, F sub s, is equal to the weight of the water. That's when it's in equilibrium. It'll stop rising. It'll just continue up in the tube to the elevation that it's at, delta H. So we can rearrange this equation to be equal to delta H is sigma pi d cosine of theta, gamma pi d squared divided by 4. And that's just rearranging to solve for delta H. All right, so if we substitute in the known values for that, by the way, we can rearrange this a little bit. We can move the 4 up to the numerator there. So we'll move the 4 up to here. We can cancel out one of the d's because we've got d in both the numerator and the denominator. So we'll take that d out. All right, and pi is in both the numerator and the denominator, so we can eliminate pi. So now we just have to substitute in what we know for the surface tension constant is going to be 0.073 newtons per meter. The cosine of theta is going to be equal to 1 and times 4. Okay, divided by the unit weight of water, 9790 newtons per cubic meter. And the diameter here of the glass tube is 1.6 times 10 to the minus 3 meters. So this is telling us how high it's going to rise when it reaches equilibrium, and it works out to 0.0186 meters. That's 18.6 millimeters. Were there any extra copies of the notes? One back here. Thanks. All right. Well, let's do an illustration that shows what effect the diameter has on how high the water level can rise. Because if it's a big diameter tube, you're going to have more surface tension force pulling it up, but then you're also going to have more weight. So let's just find out how high it's going to rise as a function of diameter. We'll solve this as a spreadsheet illustration. Any questions before we move into the spreadsheet about the calculations that are shown on the whiteboard?
Where's your angle?
Uh-huh.
For, I guess, other liquids, would there be different?
Yeah, there are. And that would be given in the problem statement, or it's something that you can look up. But water, it's 0. The wetting angle for mercury, I don't remember offhand what it is, but the interesting thing about mercury is that if you put a glass tube down into mercury, rather than trying to maximize contact with the glass tube, it would actually try and minimize contact with the glass tube. There's more of a repulsive force. So if this is mercury, and you put in a glass tube like this, then what it would do is it would be down here, but actually, instead of having a contact angle of 0, it would be looking like this, really. And so the surface tension is forcing the mercury downward into the tube. All right. So what I'm going to try and illustrate here in Boy, they've really changed things around in Excel. There we go. Thank you. All right, so we're going to solve this by having in the surface tension constant, the unit weight of water, wetting angle, all right, and then we're going to have, boy, this is so laggy. They really need to turn these animations off. The diameter in terms of millimeters. And what we just had for this example was 1.6 millimeters. All right, and we're going to try and calculate what is the delta H in terms of millimeters, how high it rises as a function of different diameters. And so we're going to basically just recreate this example we worked in the spreadsheet. And so we know from this formula that it's going to be the unit weight of water is 9790 newtons per cubic meter. The surface tension constant was 0.073 newtons per meter. And the wetting angle here was 0. We don't really even have to put that in, but the delta H then is going to be equal to the surface tension constant. I'm going to anchor that by pressing F4 so that when I drag it down it continues to refer to the same location, times the cosine of the angle, and our wetting angle is here, 0. I'll anchor that so that when I drag it down to other rows it continues to look in the same spot, times 4, divided by gamma, so the unit weight of the water, anchored, and then times the diameter. Now remember, this diameter is in terms of millimeters, so I need to have the diameter divided by 1,000, because now that'll put it into meters. And then I want my delta H to be in terms of millimeters, so I need to, whatever result I get, multiply by 1,000. So I divide by 1,000 and multiply by 1,000. It's kind of canceling it out, but it gets 18.6 millimeters, which is exactly what we had on the board. So let's say, what if it was, instead of 1.6 millimeters, what if it was 3 millimeters? We can drag that down and see that it's going to rise not as high as it did. It's about half as high as it rose when it was 1.6 millimeters. And so think about why that might be. If we made it bigger, then the surface tension force is increased, right? Because surface tension is a function of the diameter. So if we make it a bigger tube, then the surface tension force went up. So why is it that there's less water inside of the tube? Why it's not rising as high? It's not actually the same amount of water. If you look at the surface tension, if you increase the diameter, that'll increase the surface tension. But if you increase the diameter, you're increasing the water, the weight of the water according to d squared. And so if you have, if you double the diameter, that will double the force that's going up, but it'll have 4 times as much water weight, and so that it won't be able to rise as high. And so consequently, if you have maybe 0.1 millimeter, then the water is going to rise very high. Now, one interesting application of surface tension is in soil, actually. Are any of you taking soil mechanics this semester? When do you take that? Next semester? All right. Well, one of the things you'll learn in soil mechanics is that the voids between soil grains are very, very tiny and they're interconnected. If I was just to represent like what it looks like at the interface of the air and the soil, so here's the ground, And underground, if you go deep enough, you get to the water table. All right, and so let's zoom in on some of the soil. Like, what would we actually see if we zoomed in? There's going to be all these soil grains, and I'm drawing them as circles, but really, in reality, they're irregularly shaped. You know, a grain of sand is jagged, and it has a very strange, irregular shape, and it's random. And there's some that are small, some particles are small, some particles are big. There's a distribution in size, there's a distribution in shape, and so that even if you go down to, let's say, Miami Beach, which has a very fine sand, some of the grains of sand on the beach are going to be really, really small, some of them are going to be big. There's a huge distribution in size. And the same is true not just of sand, but it's true of clay, that there's a distribution of soil particles. It's true in gravel, that in a natural system there will be small pieces of gravel, there will be large pieces of gravel. So here we have all these different soil grains that are packed together. Now the water table means that beneath this level, all of those little spaces, the gaps between soil grains, are full of water. Now above the water table, it's not that there isn't any water, it's just that some of these voids, as they're called, it's a void. The void can be full of water, it can be full of air, or it can be partly coated with water. There can be a layer of water, like wetting the soil grain, because remember what we said is that water is attracted to SiO2. Well, SiO2, glass, is made out of melted sand. And so if this was sand, soil grains have SiO2, and so there is an attractive relationship between the water that's in soil and the soil grains themselves. And so think about, there's a small layer of water covering each of these soil grains, and some of the pores are going to be full of water. And so if it is a very, very small void, then that acts like it's a glass tube. Like the pathway that we're showing here, and now we've got to a big gap. So probably it would only, if this was zoomed in on here, the water level, although all of the voids are saturated under here, so below the water table, voids are saturated. Above the water table, there can be these long routes that water will rise up above the water table, because just by statistical probability, some of the pathways are going to have connected really small voids. There may be some routes that just by circumstance there would be a big grain on top of another big grain on top of another big grain, and so that the voids around them would be large. But one interesting application of surface tension is that it can cause something that's called capillary rise in soils, and so it keeps the soil moist even above the water table. And that's something that we'll talk about in hydrology if you choose to go through the sequence of fluid mechanics, hydraulic engineering, and then as an elective in your senior year, hydrology. So that's all I have for you today. Let's take one final look at the announcements before I let you go and I get started on reconciling the homework assignment. Remember that you'll get an email from me today with homework 2B. We've got a lab today at 2 o'clock. And for the lab at 2, I think that we're all going to be able to be in there. I said that sometimes we're going to split into 2 different groups. For today, everyone can come right at 2 o'clock. We're going to be able to finish probably by about 3:30, if not a little bit sooner. And I don't have the handout for you yet, but there really isn't anything you need to do to prepare in advance for that. I'll just give you the data collection handout when we get together at 2. We'll meet in the lab, the same place that we had our gathering last week, and you'll need to submit the assignment that I gave you, the lab assignment, at the beginning of lab at 2 o'clock. So any questions about that? All right, so then I'll see you at 2 for lab.